Okay, more examples. This is still 5.1. More examples of solving systems of linear inequalities. So we're going to do a couple more examples. Solving system of linear inequalities graphically by hand. And again, I will typically use the by hand method. I will, once it gets to the end of these notes, show you how you can do them on your graphing calculator, TI-84. And it's up to you. I don't usually use it because I actually think the graphing calculator is a little cumbersome. Students like it, so I will do one example and you can use it or not use it. It's up to you. Alright, so again, the solution set is any pair, any two variable pair, that makes the inequalities true for every inequality in the system. Right? And again, it's the bounded, we always do equal to, so it's always the edges, and then whatever's left unshaded. So remember, we shade in the side we don't want, we leave the side we do want unshaded. Alright, no problem will usually stay there, unshaded region. But if you solved it the other way, you still get the same area, you just have to know how to translate it into what we're looking for. Alright, so this one's an example of a system with two inequalities. One of them's a greater than, one of them's a less than. They're always equal to's. First step is to graph them. So I'm going to kind of do my scratch work to the side. So graph, so the very first one I'm going to graph would be the negative x plus y equals negative 4. And I like to, you can find any point, as long as you find 2 points, that's how you graph a line. I like to find the intercepts, so the 0 for the x and the 0 for the y. And so the first point that I have listed here is when x equals 0, well, what's y? When I plug in 0 for x, y comes out negative 4. So 1 point is 0, negative 4. And then this one is the y is 0, what is x? Well, that one's going to require me to do a little more work. Because when I put in 0 for y, I have a negative x equals negative 4. I have to get rid of that negative, so x equals a positive 4. Alright, so the 2 points I'm going to use to graph that line are 0, negative 4, and 4, positive 4, 0. Alright, so positive 4, 0 is here. And then 0, negative 4 puts me down here. And again, there's graph paper on ReggieNet that you can print off. It's just easier with graph paper, and I encourage you to get a straight edge, like a ruler or a nice sharp straight edge that you can use. It just makes it a little easier to graph it. When I usually do this in a regular lecture, I have a big ruler that I use. I don't. Wish I did, because my lines are always going to come out. I can never draw a straight line, but I'm going to do the best that I can. I'm going to draw as straight as line as I can. Alright, so there's equation 1 drawn, one of my boundaries. And then I'm going to figure out which side. I'm not going to shade it in, I'm just going to indicate which side. So I'm going to do a test point. This time I'm only going to test 1. 0, 0 is always a good place to test, so I'm going to pick 0, 0 as my test. 0, 0. I'm going to plug it in the inequality. So the inequality, remember, is greater than negative 4. So when I plug my 0, 0 in, I get 0 there, greater than or equal to negative 4. Well, that's true. And if you're unsure, if you picked a test point on the other side, it should come out false. Alright, so actually I'll just go ahead and do that. I'm going to test now something on the other side, so maybe I'll pick the point 0, negative 6. So if I plug 0, negative 6 into that, well, x zeroes out. Y is negative 6, so I get negative 6 greater than or equal to negative 4, and that's false, right? Negative 6 is not bigger than negative 4, right? If you owe somebody negative 6, if you owe somebody $6, that's worse than owing somebody $4. And so this is the false side. And so what I usually do is I'll indicate this is the side I'm going to end up shading on. But since I know I have to graph another line, I'm not going to shade it until the very end. But I know I've got to shade below that line. Alright, and so there's the first one. Now I'm going to graph the second one, and I'm going to do my work on this side. So I'm going to do it, and always colored pencils are just nice. So if you're doing this on pen and paper, or if you're doing it on a tablet, just make sure I always think it's easier if you do different colors for each one of your lines. So my first line I did in blue, the second line I'm going to do in red, so I'm going to put 1, it should be 2. So x plus 2y equals 10, and again I will use my intercept, so I'm going to use 0s for x, 0 for y. And so when x equals 0, I get 2y equals 10, so y equals 5, so 0, 5. And when y equals 0, x equals 10. Alright, so there's my 2 points. Alright, which 0, 10 is off my page. I didn't give myself a big enough graph, so since it's not on my page, I'll actually pick a different point to graph. So I'm not going to use it. You can use it, it's fine. But I didn't give myself 10, and I want to make sure... actually, I'll just go ahead and use it. I'll just have to... I wrote it backwards. Should have been 10, 0. I'll just have to go over, kind of guess a couple dash marks. We'll say that's 10. And then 0, 5 puts me here. Alright, so connect the dots as best I can. And so there's my equation 2. Right, now I have to figure out which side I want to shade on my equation 2. Alright, so test. Well, I can test 0, 0. It's on... So I'm plugging it in here. So plug 0, 0 in. I get 0 less than or equal to 10. That's true. So you can stop there. I know on the side with 0, 0 it's true, so it should be false above it. But if you're unsure, you could always pick a second test point. So pick a test point above it. So maybe I'll pick 0, 7. Alright, that's above it. So I'm going to plug 0, 7 in. So x zeroes out. So it's going to be 0 plus 2 times 7 less than or equal to 10, which comes out 14 less than or equal to 10, so that is the false side. Alright, which means that's the side we're going to shade. Alright, so I'm going to shade above. So on the red one, I'm shading above it. On the blue one, I'm shading below it. And so now I'm going to go ahead and shade. Alright, so remember, these are all of the stuff I don't want. Anything on that side of my red line. And anything below my blue line, those are the false statements, right? Those are the ones that we don't want. We're blocking them out. Everything that's left unshaded, so this sort of triangular wedge here is left unshaded, right? Those are all solutions to my system. If I plug them in, it will make both of these true, right? This is my solution set. And also anything on my lines, anything on this edge of this red line and this edge of the blue line. So I pick any point just on those two pieces. So on the edge here, so where it's kind of open. And they're infinitely many, alright? They're infinitely many points, it's open. And so this example of it's unbounded, alright? So this is the solution set is infinite and unbounded, right? Because it goes on forever. Unbounded means this is shooting forever, it's growing forever, or that mouth is getting wider and wider and wider forever, so unbounded. Alright, so there's an example of an unbounded set. I believe the next one I'm going to do is a bounded set, which we prefer those when we get to applications, but they're always bounded. Alright, so the next example should give us a bounded region. Alright, so this time I have 4, and this is actually the way a lot of the applications will be. When we get to, that's in 5.2, when we get to applications of systems of linear inequalities, which we call linear programming cases. And what we want to find in those cases, it turns out there's a very important theorem. We want to find corner points. So I'm going to look at the bounded. This is going to be unlike this one, which is unbounded, right? Unbounded case here. This one's going to come out bounded, and I'll explain why it's bounded, meaning it has an edge on each side. And we sort of force it by having these. Right, and you'll notice that those are the exact same two equations that I had in the previous example. Right? But I added 2 more to it. So I'm going to graph those 2 lines exactly the same. And in applications, this is often, we'll always have these because we'll be talking about items, things, time, materials. And so if X represents time, it can only be positive. If Y represents the number of people, it can only be positive. And so when we get to applications, most of our applications will include what we call these 2 sort of standard inequalities. My Y has to be bigger than 0 or 0. X has to be bigger than 0 or 0. It's kind of like the domain of these functions. Alright, again, I'm going to leave the solution set to be unshaded. It's going to be a bounded system because, again, this sort of forces it to be a bounded system. And I want to find the corner points, and that's going to lead us into, because we're going to find corner points is really important in the next set of notes. There's a very important theorem that goes, alright, so if I remember my graph from before, my first line, which was my blue line, went through the points, if I remember, went through the points 4, 0, and negative 4, 0. So 4, 0, and negative 4, 0. so there's my equation 1, which is the negative x plus y equals negative 4. And remember, we shaded below that line. Alright, so I'm going to keep that in mind. I'm shading below. Alright, the second line, which I'm going to draw in red, went through the points, and I believe I did give myself a bigger graph on this one. I gave a smaller one on the other one. 0, 5, and 10, 0. So 10, 0 puts me here. 0, 5 puts me there. Like I said, I cannot draw a straight line to save my life. Okay, so there's my line. There's my second line, which was the x plus 2y equals 10. And we wanted to shade above that line, remember from the last example. Right, the two new pieces, run out of colors, let's do pink. So let's do the y equals 0 in pink. So y equals 0 is the x-axis. Alright, that's this axis here. That's the x equals 0. And I want to stay positive, right? I want to be bigger than it. And so I want to be above. And so when I'm going to go to shade this, I'm going to shade everything below it. I don't want any negative y values. And so I'm going to shade below. Alright, now I'm going to pick a different color for, let's do green. Alright, green for the x equals 0, which again is the y-axis. So this is this right here is the equation x equals 0. And I want to be, so this is the opposite of the one I did in the previous video. I want to be bigger than 0, which means I want to keep the positive side. I want to get rid of the negative side. So I'm going to shade on this side. And in applications, that's almost always going to be true. Almost always. You're going to shade below the x-axis because I don't want any negative x values, and to the left of the y-axis because I don't want any negative y values. Alright, so now I'm going to do my shading. So that's where I'll start with. I'll shade with the axis. So I don't want anything on this side. I don't want any negatives on the x, and I don't want any negatives on the y. So everything below that pink line gets shaded. Alright, now I'm going to look at the blue. I want to shade below the blue. So this side of the blue line gets shaded, and everything on this side. And then the red line was everything above the red line. So everything above that red line I don't want. And so everything up there gets shaded. Alright, so what I have left is a bounded region. A bounded means it's completely enclosed by all of my graphs, and it is. So if you look on it, there's this edge here, this edge here, that edge there, and that edge there. If I can draw a good edge. And then it's that open area in between. So everything on the edges is a solution to this system. Makes that system true. I pick anything on the edge of that weird kind of trapezoidy looking shape. And then if I pick any point in here. Right, and so that's what I mean by bounded. Meaning it's completely surrounded by shading. It's got edges on every side. Unlike this one, which was open. There's no bounding on this side. It's open. But we forced it to. That's why in applications we'll do this. We'll force it to. We'll force it to be bounded by saying we have to be positive. Right? We can't be, I said that was x equals 0. That was supposed to be y equals 0. It has to be on the positive side in the first quadrant. Alright, so there's the bounded region. Right? Completely enclosed. And then what we're going to get to is we want to find corner points. We're going to get to a very important theorem when we go to solve applications that tells us something important about the corner points. And so this is just practicing finding it. There are corner points. In order to be a corner point, that point has to be on the edge of my region, edge of my solution set, and it has to go through two lines, at least two of my lines. Alright, and so there are 4 of them. There's a point here that's a corner point. I'm going to call it A. There's a point here that's a corner point. I'm going to call it B. There's a point here. I'm going to call it C, and there's a point there, D. Right? In order to be a corner point, so on the edge of the solution set and go through, if you can read that, go through at least 2 lines. All right, so the first one here, A, that's that 0, 0, right? A is 0, 0. It goes through the pink line, which is y equals 0, and the green line, which is x equals 0. All right, so A goes through the line x equals 0 and y equals 0, right? It's the coordinate 0, 0. B is on my axis, so it goes through the green line, which is x equals 0, and then it was also on my red line, which was the x plus 2y equals 10. So it goes through x equals 0 and the line x plus 2y equals 10, and it was the point 0, 5. C was the point here, which if I did a good job graphing it should, and I'm going to have to check it because in case my lines didn't come out right. And so it looks like it's at 6, 2. So C looks to be at 6, 2, but I'm going to check it. It goes through the red line and the blue line, so it's going through the line x plus 2y equals 10 and negative x plus y equals negative 4. I believe it's 6, 2, but how we kind of check to make sure it is it has to solve the system x plus 2y equals 10, negative x plus y equals negative 4. And you can solve it however you want. I think the easiest thing is just to type it into a matrix. And so that's what I would do. And it should give you the RREF when I do that. And it does come out 6, 2, so that was the correct. And it's just to check to make sure, in case I didn't graph it real good, and on this tablet sometimes it is hard to graph, it might not have actually been where I placed it perfectly on the graph. Alright, and so you kind of check it by making sure, or if you wanted to, another way you could check it is plug it in. You could take your 6 and your 2 and plug it in. So if I plugged it in, if I plug 6, 2 in here, I get 6 plus 2 times 2, which equals 6 times 6 plus 4, which comes out 10, and that checks. And then you check this one, negative 6 plus 2 does come out negative 4. And so that's another way you could do it too. You could just plug and chug to make sure your point is the right point. All right, the last one, D, is a little easier because it goes through the pink line, which is y equals 0. It goes on my axis. So, and the blue line. So y equals 0, the blue line, which was negative x plus y equals negative 4. And that was the point for 0. And technically you should check all of them. I didn't check these because those were points that I used to graph and I knew they were on the lines. Right? I knew 0, 0 is x equals 0, y equals 0. That's the only possibility. I use 0, 5 as my graph, and I use 4, 0. That is why when I do graph these, I always use these because a lot of times these are what we're going to be looking for. We're going to be looking for corner points. And often, the corner points land on my axes, because axes tend to be a part of my bounds. And so what we do is we'll so I've already found them. Right? I've used them to graph, and I've already found them. And so it just makes it a little easier. And so there's my corner points. Right? Now again, in order to be a corner point, I have to exist on the edge of my solution set, and I have to go through 2 of my lines, which that's what creates the corner, by going through 2 of my lines. If you look, we call them corner points because that's what they create. They kind of create a corner when they go through both of my lines, when they intersect 2 of my lines. And there's a reason why we do that, and we'll talk about that in 5.2, why we need that. That is an important theorem that we're going to get to about corner points in my solution set. Alright, so we will stop there. The last thing I am going to do, which I'm going to do in the next video, is to show you how you can... So I've been doing this by hand. I actually think they're easiest to do by hand. But I will show you how you can, one time, I'm going to show you how you can do it on your graphing calculator. And feel free to always use your graphing calculator if you want. Like I said, I will be using it by hand because I personally think it's easier by hand. But once you see the calculator, you may always use your graphing calculator, and that's the next video.